I want to welcome everyone who's here on the University of Michigan campus and those who are joining us online to another Saturday Morning Physics. It's the first Saturday morning in April. It is Earth Month, and we are 3 weeks to Earth Day. I'm physics professor Tim Chupp. I'm one of the organizers of Saturday Morning Physics, and we always take the opportunity to thank the people who work so hard to make these happen. So I want to note again Carol Raybuck, who greets everyone. And Monica Wood and her staff of the Warren M. Smith Demo Lab. Before moving to today's presentation, I want to remind you that Saturday Morning Physics is made possible by you, by the many generous contributions of Saturday Morning Physics fans. And thanks so much to those of you who are helping support and sustain Saturday Morning Physics. Saturday Morning Physics is also grateful to have the support of several endowments, the Dr. Mary Lois Tiffany Endowment, the Hideko Tomozawa Endowment, and the Pulakeshi Dayalu Astrophysics Fund, and also the Van Loo Family Endowment. The Van Loo Family Endowment sponsors a special event, which are presentations given by graduate students doing cutting-edge research in science, technology, engineering, etc., here at the University of Michigan. And that will be next week, and we will have 2 graduate students presenting their work on detecting dark matter and exploring and measuring dark energy in the universe. So don't miss that. Before moving on to today's presentation, I want to note that the event will conclude with our traditional question and answer session. And for those who are joining us online, and in fact those in the room, we will have microphones here in the room, but also you can send your questions to physics@umich.edu. So it's my great honor today to welcome Professor Theodore Goodson, who's the Richard Barry Bernstein Professor of Chemistry at the University of Michigan. And it's a particular honor because today is his birthday. Ted grew up in Indianapolis, Indiana, and he received his Bachelor of Arts degree in Liberal Arts from Wabash College, also in Indiana, in 1991, and his PhD from the University of Nebraska. He has held postdoctoral positions at the University of Chicago and Oxford University before coming to Michigan, first to Wayne State, and then in 2004 he came to join the chemistry department here at the University of Michigan, and also joined our Frontier Center in optical ultrafast science called FOCUS, which is where I first got to know him because I was part of that as well. He has a significant laboratory. You'll hear about the research in that laboratory. 18 researchers from fields of applied physics, electrical engineering, chemical engineering, physical chemistry, and math, among others. It's very impressive. Professor Goodson is admired for his scientific leadership and also for mentoring graduate and undergraduate research students in his labs and his contributions to their career developments. He's received a number of awards recognizing his research, including the Experimental Physical Chemistry and Percy Julian Awards from the American Chemical Society, and many other recognitions. So please join me in welcoming Professor Ted Goodson, who will tell us about organic optical materials from solar cells to light-emitting diodes.
Thanks, Tim. And thanks for all of you for being here. I know some, including some members of my family, are watching this by live stream. Tim was so nice. He said, this is 3 weeks from Earth Day. I guess it's the first week in April. And, he was grateful that you all came out on a rainy day. But there's actually another little event happening outside that he didn't mention that I thought he was very coy in mentioning, and that you came in here instead of out there to listen to physics. And what a relief, right? We can have fun and talk a little bit about physics and materials, and that's what I was going to talk to you about today. I'm really interested in developing new materials based on physical insights, developing new minds, mentoring great minds, more often smarter than myself, and getting to the next stage. And so I'm going to tell you a little bit about one of the aspects of the research that we do. We do a number of things. Tim was correct. We have a lot of different types of research going on in our lab, which requires people with different expertise, different kinds of courses that they might take, different kinds of experiences. So we, as he mentioned, we have electrical engineers, we have, mathematicians, we have chemists. After all, we're in the chemistry department, and we have, physicists. Oh, by the way, we have physicists. And, but when they're doing the research, nobody knows who is who. I think that's the biggest unique aspect about our research laboratory, is that sooner or later, they're going to figure it out, okay? The chemist is going to figure out what that physicist is talking about, and the physicist, while at the beginning might ignore the chemist a little bit, is going to realize, okay, I'm going to listen to you today, and tell me what's happening in this molecule. And so I'm going to tell you a little bit about that. And so I picked a topic that has kind of a complete story. Research is in that, isn't it, right? Research is not finished yet, right? It's not ending. But I can tell you my version of the story today. And the version of the story involves the quest to make organic solar cells, and, which ultimately led to, in the same kind of materials, the quest to make organic displays. And the physical chemistry, the physics, is very similar, okay? And the materials actually turn out to be quite similar as well. And so I wanted to talk to you about that today. And you might say, well, okay, it's a little, we're going to have a lot of physics, we're going to have a little bit of materials, but it's a little practical as well, right? So, this is a picture that was, taken and posted on the web, some 10 years ago. And this is a more recent picture. But this has been around a while. It's now to the point where you can start asking real questions. Can we ask real questions about what's happening with this field and what's going on? And what do scientists need to do to get to that next level? That's what I want to talk about today. So, you've probably seen this before. This is Ann Arbor 101. Solar energy. Lots of people have this in this town. And it's usually made with silicon, right? And that you have some strongly absorbing, pure silicon material, goes through some kind of control device that can actually collect and turn this into some kind of current, voltage and current kind of control, and then you can power up your refrigerator. That's no secret that we have those now, and it's still pretty costly. This was a slide that was made back in, some time ago, at least 2015. And to compete with those kinds of organic solar materials, people knew back then what was required and what was available. So in 2010, we're talking, pretty expensive, $30 to $50 per meter square device, okay? And the colors are pretty limited. The power is low. The lifetime, it was not very good, okay? And the efficiency not very good as well. And the market was not very large. About $1 billion, probably much less. That was being overestimating, and back in those days. You really didn't have a lot to compare it against either, okay? And, you know, today, yes, there's lots more. There's a lot more to this market, you know, a lot more expected of what's to come. And so, you know, if we're talking hundreds of billions of dollars, then maybe it's worth it for us to be thinking about that. So I'm kind of laying the groundwork that there's still room for improvement, and there's certainly still room for opportunities. On the same kind of applied research kind of token, organic light-emitting diodes, you know, have a market that's also equally as large. So it's practical to do this work. That's a plus, okay? It doesn't have to be practical. We're scientists. We're always teetering on that balance between doing something that's practical and doing something that's important, but not necessarily practical right in your face. Here, both are here. We're going to do something that's important, and then the practicality is right in your face. It's $1, right? It's $1 amount. So there's the case, okay? And so the promise is that, can you make new materials that can compete with silicon, compete with others that are out there? And the point of this talk today is that you must understand what's happening. So, you know, without understanding the physics, yeah, you probably could do something. Go ahead, okay? But we contend that you need to understand the actual process of what's happening to get to that next step. And that next step, we think, will take us into the new generation of devices and the new generation of solar energy. Okay, and so, you know, people are doing these kinds of things. I mention these at this point is that there's always a tendency to kind of get started with like the engineering of new devices, which is reasonable, and so I have, Tim might have alluded to that, I had started a company to actually look at new materials for devices in the military, medical, and automotive sector, collaborating with these companies. I mentioned this before, you know, this was a company that we had started to look at new kinds of devices for supercapacitors as well as light-emitting diodes. But I'm not going to talk about that today. I'm really just going to talk about the science behind it and how our understanding has improved, hopefully now, to get us to that next level. But at the heart of everything is all about light. And so before we get too far into the applications and the detailed science that I want to tell you about today, let's talk about a few things. I hope I'm not going to get shocked or anything when I push this button. Okay. Oh, there it is. Okay. So we really leverage the properties of light. Whether you're talking about some fancy femtosecond laser or just the white light, we leverage. Like going through a grating and an interference pattern, as you can see there, and then seeing the distribution of interference. As just by going to something as simple as a slit, you can see that light has lots of interesting properties that can be leveraged by scientists to do new things. And you can try this with 1 and 2 slits. What I'm trying to show in this slide here is that, you know, light can be manipulated. You can talk about reflection, you can talk about the interference. And now Monica can show you some other kinds of light, but I guess I need to turn this off. We're leveraging the properties of light.
So all of you that are here got the diffraction rating.
This is like a 3D movie.
It is.
So now put on your 3D glasses.
You should be able to look at this light and see the rainbow off to the left and right of the straight line in your view. Those online will be able to see what they're seeing through the camera output. Oh, sorry. Sorry about that. So you guys should be able to see a vertical white line, and then to the left and right, you should see a rainbow. Those online are getting the same view that the people in the audience are getting, which again is that white light produces the continuous spectrum.
Yes, white light has all the colors. And you're using a grating. And the grating's made out of some plastic, a polymer, or an organic material. And it's actually just separating those wavelengths. And so the white light has them all. Or you can have discrete energies. For example, hydrogen. It has this beautiful color. Oh, you can't really see it. It's a pinkish color, but you can't really see it too well. Oh, yeah, you can see it on the right, but the color in the actual vacuum tube, you can't see that. But you can see the colors of the line spectra of hydrogen, so-called line spectra. And then helium, you can see its lines. And you can see that yellow one there, as you can see that Monica has illustrated there with helium. These are gases fitted inside a tube with a discharge. And they're actually being excited through discrete energy levels. As opposed to the white incandescent light, which has all of them. This is the discrete energy levels, and I think she has one more. And the final is neon, which has perhaps the most sophisticated spectra, right? You can see more lines. Okay, so before you show that, I mean, what's happening in there is so-called, so when you trap the gas in there, the Balmer series, or so-called the spectral lines, can be calculated. And these bands of lines help us understand the energy states that the gas, the material, are occupying. And we're looking at emission from those states. It's trying to get you to first think about, kind of get your mind in the idea that things like molecules and atoms, they have energy states. They have electronic energy states. And the demonstration that Monica has shown you, that they can actually be, their lines and spectra can be predicted by using, Rydberg equations, and you can calculate where those states are for things as simple as like gases, like the Rydberg gases. And then, of course, the final thing is that all these molecules, all these things, all the light has a characteristic wavelength. And so we're after that. We're going to leverage that. And I think she's going to show you, when we leverage the wavelength of light, we take advantage of that. So I don't know if this is...
This is using a spectroscope.
Okay. Right, you can see the spectrometer. So a couple of things are here. So again, this is a gas that's giving off particular discrete energies. This is a camera, so you guys can see the color, I guess, on the television. But then also this ocean optics here. So ocean optics makes this spectrometer. It's going to measure the different wavelengths of emission that comes out. And this company here, this ocean optics, has really revolutionized how to make these things really small with fiber optics. Inside this device here is a grating and all the things necessary that normally we would use this kind of size for a spectrometer. And so this is using, some really small kinds of IC technology. The light is being scattered off there, and then you see the spectra. De Broglie and others said, all matter, all particles, all things have some characteristic wavelength, and we will leverage that today. So those are the kinds of things we want to kind of get started with. But what about our inspiration? Yeah, our inspiration for this game that we're going to play in the solar business is the actual nature. So we're inspired by nature. Why? Well, actually in nature, the efficiency the process is perfect. Are you surprised? What I mean by that is that the absorption of photons and the transfer of energy absorbed to something useful is near perfect, near 100%. The absorption of photons from light into these photosynthetic chromophores, this is a cartoon, okay? So this is the real leaf, okay? And this is a cartoon. I mean, someone has taken the leaf and grinded out the protein inside the leaf and says, what makes the leaf grow? Oh, the leaf needs a photon of light, and it ultimately needs some kind of food to feed itself. It transfers that photon of energy into food somehow, and this is how it works. And so it says, well, it takes a photon of energy and absorbs, and it has this kind of ring-like structure of molecules. It's really interesting. It's the little things that matter. In the natural system, these green squares, they're dye molecules, pigments. I don't know how else you want to call it. Okay, I mean, they're there to absorb the photon of sun. Okay, the photons of sun, but they're not actually attached to each other. It's the little things. They're actually not attached. They're attached to the protein. So these are all pigments, and this molecule is all in one big protein. Okay, and they're not attached to each other, but they're really close. Okay, maybe there's a reason. And it's in a circular geometry. So what happens? The light comes in, the photon comes in, its energy is too high. So it gets absorbed onto one of these green squares, one of these pigments, and then it transfers that energy around this circle, and the energy is now lowered. It's worth explaining this to you. You're going to get the rest of the talk, okay? And then it will hop to the next ring. It's almost like it knew the photon when it comes in from the sun to the plant. The energy is too high. Can't do anything. No. Go away. Instead of wasting that photon, it says, well, I'll develop this engineered process where I'll put the chromophores in a circle, and as it goes around the circle, the energy is getting smaller. Okay? So here's the photon. It goes around the circle, and the energy is lowered. And then it hops, and it does it again. Goes around the circle. We actually know this happens now. And then finally, it gets to the big kahuna. This is actually bigger than these. And guess what happens? It's slowing down so slow now, the energy is so small, it can be used to catalyze a reaction and make 1 mole of food for the plant. It's perfect. It's absolutely perfect. And so we want to copy that. Easier said than done. But we don't want to build some fancy protein. We want to make some simple molecules. Okay? We want to make some simple molecules we can paint on the top of our house, and we'll all get rich. And so, spoiler, it hasn't happened yet. Okay? And so, but we've learned a ton along the way. Okay? So what I'm going to talk to you about is, first of all, how to try to do that in an artificial system, and what are the processes. I guess you've already figured it out. We would like to have a process in which the energy is shared amongst many, to do the energy transfer, to absorb the photons, and then transfer to the trap. That's what we want to do, and we'll see how successful we are. So what do we do, though? Let's be careful. When I give this talk, usually people assume we're the people that make the things. Unfortunately, we don't. We study them. We study their properties. Why do I say unfortunately? Because generally speaking, the person who makes the discovery of the sample usually gets the patent, so so it's unfortunate. But it's fortunate for us that we collaborate with scientists who can make these really sophisticated molecules, and they listen to us. They listen to what we say. Here's what happened. I know what the idea was. Here's what we were trying to do. This is actually what happened. And they change things, okay? And so that's what we're going to talk about. Meng Guo was one of the very first students I had here at Michigan, and she was excellent. And so I'm going to tell you about not all the experiments that we do, just maybe about one or two, maybe towards the end. And so we do a lot of experiments with lasers, hence we're going to leverage the properties of light. We do a lot of experiments with ultrafast. We do now experiments with something called entangled photons. Today is not about the experiments, Ted. Today is about the physics, right? It's about what's the result, what happened, and that's what I'm going to tell you. So I'll tell you about one of the experiments in detail towards the end of the talk, but here I'm going to tell you what happened, and then we can talk about the physics. Okay, so it turns out that there's some fundamental thing to think about here first, and everybody can understand this. Those green squares, they know that the other green squares are there. They are so-called coupled. Their potential is strong. How many ways can I say the same thing? They are connected. They are correlated. How do you know? Well, we do the experiments and we can check that. But there's different levels of being connected, different levels of being correlated, okay? There's some levels that the further I move from you, the weaker I'm correlated, okay? The further I move from you, the weaker I'm correlated to you. That's one extreme. That's almost no correlation, okay? It means the only thing I got to do to get rid of the correlation with you is just to walk away. No pun intended about relationships and all this. I'm just talking about physics here. That was supposed to be a joke. Okay, you didn't laugh. He's been laughing at all the jokes so far. Okay, the other extreme, right, is to connect them. So the first extreme is to have no correlation. The other extreme is to connect them. That means everything the person to the right of me does affects me, and it'll affect the thing to the left of me. That's extremely strong, okay? So and then there's something called the excitonic. This is a potential. It means that it's stronger than the distance-dependent kind of thing, but weaker than the connected, right? And what we found was that there's this gray area, hence the gray box. That's where the natural system sits. It's neither connected, you saw. They're not connected to each other. And it's certainly not weak, okay? In fact, it only takes about a billionth of a second for that energy to go around that circle. That's really strong connection. But you saw they were not connected. They're not physically connected. So how to study this gray area? And it's a fundamental. That gives you the fundamental physics, new types of properties, right? So this is the idea. This is like a cartoon again. It says, look, if all the pigments have their own response and they don't know about each other, then they're nothing more than the sum of their parts. Hence, you will never make the natural system. You need to find a way such that the sum of the parts gives you something better, right? And that's what we're after, okay? We're looking for something better than the sum of the parts, but we don't know how to do that synthetically yet when we started this project some 20-some years ago. Okay, so one person who knew a lot, this is I'm going to show a lot of pictures. This is my postdoc advisor. Tim said I was at the University of Chicago. And so this is a person who was a physical chemist. It means he did, lasers and so on, who became a material synthetic chemist, who started making stuff. He changed his career, which hardly ever happens, right? So he was a physical chemist and became somebody who primarily made things, okay? And was my mentor right till this is at his retirement, okay? But he was the first to suggest that you could make organic molecules and sit on surfaces and have multiple interactions. He was the very first. And probably because he got tired of asking people, you know, look, this is a really good idea. Please make this molecule. And they're like, you got a grant for that? You know, or it was not very easy early on to ask people to do that. So he kind of pushed things, and that's probably why he got into the game. And you can see, this was his original idea, that you could have a surface, and you would put these molecules on the surface, and they would actually have this energy transfer. And we did the spectroscopy with that. I like showing this picture, it's very colorful, but the point of this is that it could measure that energy transfer, okay? Remember, we don't need this kind of energy transfer like this. It doesn't have to be in a circle. We just need the energy transfer to happen. So the early ideas were that it wouldn't be a circle, that it would be this kind of dendritic structure, like a tree itself. The energy would be captured on the outside of the dendrimer, and then the energy would make its way to the middle, in doing so, lowering its energy, and then energy trapped. So Mahinda showed that you could have this kind of energy transfer in domains of these structures using these kind of dendritic structures. And that was, as I go through these, I'm going to go through them pretty quickly. I'm going to probably point out, which I should do, why it didn't work. But each case, a PhD was obtained, right? He obtained because he saw that it wasn't like they thought. It was going to be in these kind of domains. The energy would be captured and then localized in little domains inside the big molecule instead of what you had thought that it would do, because the molecule is not planar. And so, okay? Oleg Varnovsky investigated this cyclid thiophene structure. Oleg's a senior scientist in the group, still in the group, and he showed that you could get this enhancement in the delocalization, the energy transfer, as you make the ring size bigger. And so this is up to micron scale. But in about 2008, in this project, things changed fundamentally. So a couple of scientists, one is Kabuki, started to make molecules with the same kind of pigments that's in the natural system, but they're going to, as you see, attach them. And the diameter is about the same as in the natural system. And it's a circle, okay? And so he made that, Kabuki. And Ajit Bhaskar and Jeff Raymond were graduate students that worked on this in the project. And the idea was that, okay, I'm not going to make a big protein, but I can take the pigments inside the natural system and make this circular aggregate structure. And I can measure the coupling by doing all our fancy spectroscopy. And so he did that, and we saw that you could get a good energy transfer, nowhere near that efficiency, though. Again, this is like a picture that we draw and we teach courses. That molecule is probably moving. It's not staying still. By attaching them together, you're restricting their movement. So the natural system, they're not attached. Maybe that's for a reason, okay? Today, we still look at other kinds of phthalocyanine structures. This is Sarah Jovanovsky and Logan. They've done a great job looking at these phthalocyanine with thiophene branch structures. And then we've done some ultrafast with, transient, femtosecond transient. We still are kind of struggling trying to understand how we can beat this process. This is what Juan Cabeza and Sean, where they did femtosecond transient. But here's where we're at, okay? It says that, this was our goal. We wanted to understand how we could take multi-chromophore systems and get something more than the sum of their parts. And this is a great way of looking at who's giving us more than the sum of their parts. This cross-section, which I didn't explain, just look at it as a cross-section. You want this to be big, but you want this size to be small. If you need a gigantic size to get a large cross-section, then you kind of you haven't gotten the idea. And so down here, even though some of these things are pretty large cross-sections, they actually are pretty large. Somehow the natural system, the actual number of chromophores is not that large. The whole protein is large, but the number of chromophores is not that large. But the cross-section, the better than the sum of their parts is. So what do we go from here? Well, we're still trying to understand this coupling process. It's all about the coupling in the end. It's all about that gray area. And it's not only just about solar, it's about organic light-emitting diodes as well. You know, essentially the same kind of physics as we saw with the solar. If you can enhance the coupling between chromophores, you can get larger absorption, and then you could have a more efficient solar cell. If you can enhance the coupling between these pigments, you can get larger emission, and you can have a more efficient LED. Similar idea. We had a good collaboration with LG and some of the folks at Samsung as well, and looking at materials for their kinds of applications. And I'm going to tell you a little bit about that. One of the things is to look at, when you have what seems like a display that looks perfect, there's always these defects. But even beyond the defects, we were looking for ways and to look at situations in which emission or absorption was coming from chromophores in the display that was a result of coupling between chromophores, isolated chromophores, defects, and so on. And the idea is that looking at that process will help you say something about the lifetime, the efficiency, and the usefulness of these devices. So we built this microscope. So I'm going to tell you a little bit about this microscope. And it turned out to be a good collaboration with LG. This microscope is basically trying to, before I tell you how it works, it's basically trying to look at the film, the display, and tell you how the emission originated. Simply put, when you watch your television, you're not asking such questions. You're just seeing the light come out of the display. But the LG and Samsung and other places know the mechanism of the emission that you're actually observing has something to do and will play a more important role in the stability and the efficiency of their device. And so this device can measure those kinds of things with great accuracy. I'm going to tell you about it. So one of the people that worked on this, a postdoc, Benedetta Carlotti, who's now a professor back in Italy. It uses something called a near-field optical microscope. Basically, this microscope, and it's a 2-photon, this microscope can get to very single-digit, like 20 nanometers maybe of resolution, spatial resolution, and it's in the near field. And we were starting to do this, but that's not the time-resolved part. So the time result, you might ask yourself, okay, you could see how you could make a microscope. You have some kind of tip, and you have a light, and you can shine the light through the tip. But how do you get the time resolved bit? You get the time resolved bit by doing this so-called pulse pair generation, where you have a phase-locked pulse pair. Basically, you have an ultra-fast pulse, and you put it at 45 degrees, and so now I can have both the P and S, or the vertical and horizontal polarization. But you're basically going to delay one pulse behind the other because you're using this BBO crystal, which has got a wedge. And as you can see, the wedge, this is another property of light, the property that you can delay things by the refractive index, as the thickness, the amount of thickness that the light goes through will delay one of the photons relative to the other. And so this is called this, group velocity. So then one of the photons has this polarization in the vertical, and the crystal is in the vertical, and the other one is in the horizontal. It gets delayed behind the other, and you can see you can make a delay on the order of less than a femtosecond, and then you have the output pulse. You can do this in the microscope. Okay, so you put these pulses in the microscope. But why do you want to do this? So now this is technical. So, and the way to describe this is the molecule has to respond. And I say that if the molecules are behaving like the natural system, that means they're collectively connected to each other. They will respond in a way that says, we're all on the same team. And if they behave in the way when there's weak interaction, each molecule says, every man for themselves. Hey, I'm sorry, man. You're gonna get dephased. That's essentially what we're saying. That the natural system, that the great LEDs, that the great devices have materials that somehow when you excite them, either with a pulse, either with electric field, they all say that we're all on the same team. We'll dephase together. We'll get in the same phase, such that we'll make this last longer. And that's what this picture is saying. It's in the red curve says, I'll hit the molecule in the back of the head with a pulse, and its polarization will make the molecule say, someone just hit me on the back of the head. And before it's like a cartoon. You see the cartoon person, they're doing this. Before that ringing, it's literally called ringing, ends, you hit the molecule in the back of the head again. Okay? And that's the green, okay? And these two pulses now will interfere with each other, just like the interference we were showing you at the beginning, right? And I'm going to wait to see how long that interference lasts. And the molecules that are on the same team, that interference will last a long time. And the molecules who every man for themselves won't last so long, okay? This is how we determine where the light came from. And it matters. It matters. Certainly it matters in the natural system. And when you're talking the next generation of LEDs and solar cells, it matters. So Tai-Soo Kim, who came from LG, and they sent him to Michigan to do a PhD, and he went back to LG Chemical. He set up this microscope, okay? And it has a spatial part, and it has a temporal part. This is the fluorescence. And you can see, this is the molecule ringing. Look, this is 252.9 femtoseconds. This is 254. It's ringing. You can see the image, you can't see the image. You see the image, you can't see the image. It's ringing, it's ringing, it's ringing. Until finally I don't remember the pulse anymore, okay? So this is the pulse. It's still ringing. These are the blue and the red are the oscillation. The pulse is already gone, and the molecule's still, okay? And so what does that mean? Okay, it means now, and they were interested in this, because they were sure that the quality of their device and films was homogeneous. Maybe it was homogeneous, and if you were to look at it, the thickness was perfect. This is not asking that. This is saying, is it homogeneous about where the emission came from? That's a different question, is it not? And so, look, if I go to this point on their film, I get this curve. It means that these molecules pretty much are behaving by themselves. But if I go to this point on their film, I get this curve, which means that, okay, it looks like there's some aspects of behaving by themselves, but then I see this kind of peak like that. That different mode suggests to me that there is some kind of long-range dephasing. That means these films are very, very good. it suggests that even in a perfectly looking film, when you image in terms of the time, in terms of the coherence is what it's called, the ringing, it's not perfect. And we've done this for a number of different, that's organic, and the perovskite kind of films, Federica did this, where she looked at a single quantum dot, and you can measure the actual coherence, you can measure the fluorescence that comes from. We're actually really interested in where the fluorescence came from, rather than where it's going. Then Chanchal Rani, who's an excellent postdoc, her paper was on the cover of this journal, said, well, let's get back to the physics. She's a physicist. And she's working with Elizabeth. And they said, well, all games aside, let's just put some small number of molecules inside a sphere and look at how coupling between the small number of molecules, and we'll change that systematically. And she measured that dephasing. Sometimes we have to go back to the beginning to go forward. And then Oyusayo said, well, okay, you can actually look at the light-emitting diodes and talk about the efficiency, but there's other methods and mechanisms that you can look at. He's looking at this thermally activated delayed fluorescence mechanism. It's saying, well, if you can't really get to a situation where you can have this kind of coupling in your organic system, maybe you can use that same organic system to look at different mechanisms of how they couple. And he and Ricardo, who's now professor at Indiana University, and Lloyd is at Dow Chemical, they showed that you could use this mechanism. This is the actual efficiency, and this is the lifetimes that they measured. So you can see there's some correlation between the lifetime, the rates, and the efficiencies. This is the real device efficiencies. In this case, they were working with a professor in South Korea who works with Samsung. So in the last couple of minutes, I just wanted to mention there's other ways to get at this kind of coupling in these chromophores. I don't have time to discuss it today, but we can also investigate things using not only ultra-fast pulses of light, but using something called quantum light. And a large number of the people in the group are now using this, and we have one of the first quantum microscopes to look at these kinds of couplings with extremely small numbers of photons. And so Oleg and I have this patent on this microscope, and Josephine was the first to utilize this microscope to demonstrate that you can image and see astrocytes excrete calcium in brain cells. And then Paloma got the first images, the actual images of the brain tissue with entangled photons. And Carolyn worked on that project as well. But yes, we are now looking for new ideas. We're pushing forward with new techniques. That's what we can do. We can do new experiments. We can evaluate new materials like Bo Zhao, who's in our group, is using entangled photons to think about how you can enhance the efficiency of photochemical reactions. And so we're just kind of moving out of just only using ultrafast, but also using ultrafast with the idea that we can induce entanglement as well. So I'm gonna wrap up what I have to say with these take-home messages. We still are searching and trying to catch up with Mother Nature. It literally is perfect. Lots of really good synthetic organic chemistry, and lots of really important lessons, but we found evidence that in at least one of the systems we saw that we're on the right track, that we can see this kind of coupling in artificial kind of systems. But organic light-emitting diodes and organic solar cells certainly have a place in today's market. If you're interested, you know, and the research still goes on. The reason, you know, organic materials are a good idea for this market is their ability to be tailored, so the materials can be tailored in a different way by using synthetic chemistry. They have long-range interactions that can be enhanced. You can make them flexible, as you saw in that great gigantic display by LG. It can be completely flexible. And of course, the hope, of course, is that they will be very cheap. And so, that in itself, these reasons, is that it will be around for a while. And so we have discovered that the best materials have chromophores that behave collectively, and they provide enhanced solar energy reception and light emission. This idea of collective excitations has really caught on, and it's not just making molecules in a chain. That didn't work. It's not just connecting molecules. It didn't work. It's actually something in between, that gray area, and we think we're getting close. And the gray area, in the case of the natural system, I should just keep mentioning this, is only made possible by the protein holding on to those pigments. So the future holds great promise for improvements in our understanding of the collective excitations and making new artificial systems, and I think still for improvements in device efficiencies. So with that, I'm going to conclude, and I hope I've mentioned just about everybody in this picture, and I want to thank the grant agencies that have supported this work and continue to support it. And I want to thank you for your attention, for being here on Saturday. I really appreciate it.
Well, thank you very much, Ted. And I want to thank you for pointing out and emphasizing how science isn't just science giving us technology. It's not just spin-offs of science,
Right.
but that science needs to explore the basic processes for technology to advance. That's a really important message. I also, for those of you who have the slides, and if you didn't really get a chance to use them effectively, and if you stick around after we have questions and answers, I think you can come up and we'll let you...
You just turn on the white incandescent
Yeah, we'll turn on the lights and show you how to use them in case that didn't work out for you. Okay. So we have a microphone in the room, and we're looking for questions to come in online. Let me start by asking you the following question. Okay, so a couple of questions. The particular organic molecules and the perfection in nature that you discussed was photosynthesis and chlorophyll. And evolution, I believe, has sort of picked out the right molecule for the light of the sun. Mm-hmm. In vision, there are other proteins, opsins. Yeah. And they do something a little different. They pick out special colors. But I'm wondering how opsins could affect this field.
So we are using, so it's funny that you mentioned that. We are using opsins in our two photon applications and others. Maybe a better way to say it, what all of these molecules have in common, in most cases, is they have some kind of heme group with some kind of conjugated bit, okay? And the opsins and other molecules have that kind of geometry. It's the tailorability part that allows them. For in the case of the natural system, it's tailored to about 780, 800 region, nanometers. And the opsins is tailored to, for us, I think, somewhere around 500, 530. So again, one of the advantages of organic materials is that you can tailor that wavelength, right, to what it absorbs. People have tried opsins for this natural, you mean for like solar cells? It's in itself probably not, right, because the spectral is not very broad. So what you want for the solar is you want to have some kind of system where the spectral will get really broad quickly. And so for applications in eye imaging and things like that, opsins are very popular.
This may be a kind of a peripheral question, but one of the perfections of the leaf gathering the energy and transforming it is that at the same time it's a perfect system, it's also not harmful to its environment. So my question is, in the materials that are being investigated now, are we getting closer to that? For instance, you know, all of our electronics, we have very toxic things in them. Are we getting closer to a natural system that isn't toxic?
An artificial system, yeah.
Yeah.
Absolutely. We're better. And a lot of the initial, thank you for that question, because a lot of initial research did use like heavy atoms and things like that, obviously, because they will absorb a lot of photons, okay? But it's not taking effect using this mechanism. But then, of course, a lot of the things that are not harmful to your question, to the atmosphere, they all kind of usually absorb in the UV kind of stuff, and that's not visible light, okay? So there's the trade-off, right? Things like truly organic, all organic materials that you would see out in nature, lots of UV absorption, not too much in the 600 or 700, right? If you're synthesizing some molecule. And so,
Capturing the energy.
well, the ones that are capturing it really well are the ones out here in the 600 or 700, not the ones in the UV, right? So that goes back to Tim's question. You want something that can take all the photons, right? And so once you start making the molecules, so I mean, yeah, there's been some improvement. Maybe there should be more emphasis on making improvements that are also kind to our environment, and you know, not only just to enhance the absorption.
Hi, that's really a really interesting talk.
Could you just...
Oh, sorry. A really interesting talk. I wanted to ask, so if this system that plants have developed is so efficient, why is the emphasis on trying to synthesize new molecules rather than trying to repackage these molecules that seem to do so well already?
You mean from just harvest them from nature?
Yeah, and then try to repackage them.
Yeah, it's a
to
little
the form factor.
expensive, right? So, yes, you would just go out and get the protein, right? First of all, it would be really expensive to make these. But to go out and harvest the protein, we make it look easy. I didn't do that. I mean, they had to, you know, they grind up the leaf and, you know, solve the X-ray structure and do all this stuff, right? And they come out with a milligram of protein or something, right? No, I mean, the scientific, I guess, way is to learn how it does it without trying to duplicate its complete structure, because the structure is really complicated, right? It's a big protein holding the pigments together.
Thank you.
Good question.
I'm going to maybe follow up maybe my question and this one, and to ask, you characterized nature as perfect. I wonder if you could quantify this in terms of efficiency. So
99 point something.
Really amazing. That's probably not the case with the opsons, right? They're not that good at all. So it wasn't such a good question I asked after all.
Okay.
Roy.
First, great talk, Ted. Really enjoyed that. I have a question about lifetime. It seems that the conditions in the gray area may be somehow in competition with increasing the lifetime, or they may be limiting the lifetime, let's say. So this is really important for solar cells, obviously. So how do you kind of get over that problem?
Right. So there's so many things that we maybe don't completely understand about the natural system. So Roy's question was that if you make a system that has the collective oscillations, you might get more efficient, but the stability, essentially, of your device may go down. And that's reasonable to think that, right? Because before, every man for themselves, right? Okay? And I got a gazillion number of molecules on this leaf, and the lifetime is good, right? But if everybody's connected, then you could imagine one thing goes wrong, right? As they say, if one of us goes down, we all go down, right? And so it's a good question. There have been good arguments that in the case of the artificial systems, by having this collective excitation, you actually increase the lifetime. Why? Molecules that are strongly coupled together may be less resistant to things like oxygen. So what can kill the device? Usually it's exposure to oxygen and things like that that cause the lifetime to decrease dramatically. And if you have a number of, you can think about these seats as the chromophores, if you have a number of them and they're all on the same team, they can deal with that contaminant, if you will, better than if everyone's for themselves. And that's been the idea. So the best device that's out there is using this idea of collective, is nowhere near silicon, of course, right? But I mean, when you think of silicon, I guess every atom of silicon in the crystal is coupled to other atoms, I guess, right? But the stability question is a little bit more sophisticated one. I'm just taking only that aspect of the stability, that if you do have coupled chromophores, that you could make a more artificially stable device. But there's all other things that affect stability. Mm-hmm.
So here's a question that came in from one of our online participants, who is from the math department, and asks, you mentioned that math plays a role and mathematicians play a role in the research. Could you expand on that?
Oh, my goodness. I did a good job today because I think I only showed one equation. Is that true? And it wasn't about the stock market. So it was about what? I only showed one equation about the wavelength, right? And so, no, a lot of this work has to do with modeling. A lot of it has to do with trying to come up with ideas about how our signals can tell us what we think we're looking at. In particular, it starts with someone coming up with a theoretical model, our colleagues at Northwestern and others, who start out with some theoretical model that says that, hypothetically speaking, I have 5 chromophores sitting next to each other under a thermal bath, and I want to calculate how the excitation will be dephased based on 2 of them having a strongly coupled chromophore system. And I want to model that process, and I use this either low temperature or dephasing. I know Elizabeth and Zhenjiao now are looking at some of the data they got, talking about homogeneous broadening and other types of broadening mechanisms. That gets down into the details of really what is actually all this about. And the models are still being developed. The models are really great for atomic systems. The models are still being developed for more useful systems that have 5 or 6 molecules or something. Understanding how energy is dissipated throughout molecules is a major theme in chemistry and physics.
Sorry, I'm not in the, with background of the science behind. But my question is that you used the 2 examples for leaves and another's OLEDs. For the leaves, it's from the lights to the energy and to nutrition. And then the OLED is from voltage to energy to light. Seems that, are you implying these 2 directions are the equivalent, or they are easily to convert with each other?
Great question. I can answer that in a number of ways. His question is excellent. He basically said, and I was trying to bait someone into that question by kept saying, the molecules are basically the same for solar and for OLEDs. And he just outlined, in the case of solar, you absorb the photons and then transfer the energy, right? In the case of the OLEDs, you apply a voltage, you give off the photon, right? It looks like the science I was just describing about how the molecule must transform itself into absorbing and how the collective excitations, it looks like the process is similar, except the the ray dynamics in the diagram is obviously opposite, right? The physics is the same, right? The collective excitation either wants to absorb, or the collective excitation when excited by the electrical charge in the OLED. Is it just one of these excited, or is it the same? Electrical charge, photon charge, very similar. I guess what I can add to that, we have another project. So to answer your question, we see similarities for electrical kind of excitation and photon excitation all the time. We have another project in which we are exciting astrocytes. These are brain cells. The previous work has all been with patch clamp and voltage excitation of these brain cells and brain tissue. And we can do the exact same thing with photons.
Here's another question that came in. I love this question, which is, imagine plant life on another planet with a different colored sun. Would molecules have developed for, let's say, a very different color, like, in the infrared, that could do the same?
Well, no, I mean, do I get to pick what color the sun is? Right? Because then we would pick the UV invisible, right? In the 400. Life would be easy. That's another complication, difficulty of living here on Earth and trying to do something artificial, right? Is that the best materials are out here in the infrared. They're not necessarily good for the planet, right? And so if I could do this on another planet, but I'm pretty sure that maybe the person who wrote that is not asking, because that would have been the obvious one, right? So yes, so if the sun turned like a different color, the advantage of organic materials as opposed to others is that I can just literally tailor the wavelength. And maybe if the sun was purple, I could tailor it in the UV. If the sun was, pink or whatever, tailor it in the near infrared.
So as the complexity of the proteins increases, the cost clearly increases. But as the proteins become more basic, it's hard to force them together, and the connectivity decreases. So how are you decreasing? Does the size of the system force the more basic proteins together, or how do you increase the connectivity of more basic proteins?
Okay, great, thanks. And I think some people still are working with proteins. So if you go back to this slide where I said, look at this slide, and I said, look, in the end, you can think of, this is exactly your question, okay? And if you were a CEO of a company, and you had all the scientists walking in and telling you all these great things, right? And you say, I don't have time for that. Just give me the punchline. That's funny, but that actually happens, Okay, all the time. You would look at this picture. So the x-axis is size. This is exactly what you're asking, right? So you say, these are for the artificial systems, not the proteins, though. But let's assume it's the protein. And it actually is true. The bigger the system, the better it is. But the size is getting large, and the size is the cost, okay? And so you want something to be down in this region, but up here. Agreed? And so that's what your question is. With proteins, it's not so easy to change that. With organic chemistry and these molecules, they can, but unfortunately, they never get up to this. This is the problem. They never get up to this region. So I can, with organic synthesis, it can move back and forth across this. The hope is that they want it to be up here, and that hasn't happened yet. Good question.
That is a great question. Let me just ask this really simple question, which is, why are organic LED televisions so much more expensive?
Well, you mean
than silicon-based?
Okay, I mean, right now, this is kind of new technology, experimental, hasn't been fabricated, only lucrative by a couple of companies. There's a number of reasons. So people hope in the future that that cost will equilibrate, right? So that's one thing. So that aside, the real reason why it could be more expensive now is that, this is really high. There's a few things that organic materials seems to suffer a lot more than the silicon, and that idea of stability is at the top of the list. So the way in which those fabricate, I have one of these TVs at home, the way they're fabricated, and then they have to be sealed from the environment. There's a cost associated with that. And so, and then, I mentioned Joseph's work, getting enough light in the blue with these organic materials is a cost issue. And so naturally, it's not happening yet. It's not happening, so they're doing things and then you're paying for the cost, right? And so I'm not a business person or anything, but from a fundamental standpoint, until that stability issue is handled and pushing things into the blue, I do think it'll be more expensive.
Thanks for the good explanation. I have a question about why you decide to focusing on the gray zone instead of like complete coherent systems. I believe that you mentioned that you may get better efficiency if you have a complete correlated system. Is there any mechanical properties like the advantage?
No, we started completely. I agree with you. We started, so my first PhD ever, we were working in that region, conjugated polymers. It was not good enough. That's the result. It seems like something that was strongly coupled through conjugation was not as good as some of these systems where it's not attached very close.
So you're going to get the overall better efficiency if you have slightly loosely correlated system?
Right,
Okay.
but not weak. It's this gray area.
Thank you.
Maybe you understand this question. Is the excitation of astrocytes, as you mentioned, similar to optogenetics?
Who asked that question? So yes.
I can't say.
It's anonymous. So the excitation of astrocytes basically suggests that you're going to use a photon to stimulate the cell to release calcium. Most people were doing electrical charge. With optogenetics, you need to use light to initiate something physical in the cell or the body, right? And that's what they call optogenetics. Some process is stimulated by light. So this would be an example in which if you could stimulate the actual calcium release process with a photon of light and then watch that process as opposed to voltage.
And maybe one last question or discussion, which is, can you tell us more about the quantum microscope and what's quantum about it?
Oh, okay. So I kind of made the talk today about LEDs, but a major part of our research is involving quantum states. So without giving a complete talk, what I've talked about today is about using materials to absorb solar energy and to give off light in OLEDs. And we use a lot of laser spectroscopy with really fast pulses to probe those important collective excitation processes. In the case of a good part of our group, maybe a third or more, are using something called entangled photons. And we have this microscope which it uses, the whole point about quantum entanglement or entangled photons is that you can have pairs of photons that are so strongly correlated that the properties of one of the photons is dependent on the properties of the other. And you can utilize, you can leverage that fact that with entangled photons, they are acting together. You can leverage that to get very good, somewhat better spatial resolution, but much better sensitivity in your microscopy. So this microscope utilizes entangled photons, and the whole point is that without going through a huge talk, the whole point is that we have illustrated with the microscope that we can do these kinds of, because the noise is so low, we can do these kinds of microscopic measurements down to extremely small numbers of photons. So small that we can actually count them. The reason why that's important is that in biological systems, where you're looking at a single cell, a single biological brain cell, you would like to monitor that process for a long period of time. And in doing so, using regular light, regular laser light, you would actually photo bleach it, or you would destroy the cell. And so we have found that a way to demonstrate this, that we can image things for extremely large amount of times, because the actual cells don't even know that it's there. We're talking several orders of magnitude. So when Paloma had measured her brain tissue, and Josephine had done the astrocytes, we're talking 10 to the 7 photons. And when you do the other spectroscopy that I've been talking about today, we're talking 10 to the 20 photons. So, that's what this picture is showing, is that today I've talked really about coherence using ultrafast. We can ask similar questions using entangled photons, which is a different type of experiment.
Great. Well, I want to thank everyone here and online for great questions and for the great answers and for your presentation today. Let's thank Professor Goodson one more time.